Welcome back. In this video, we are going to solve problem 13-12 that is taken up from chapter number 13, Buckling of Columns, and book name is Mechanics of Material by R.C. Hibbeler, 9th edition. So statement is the control linkage for a machine consists of two L2 steel rod BE and FG, each with a diameter of 1 inch. If a device at G causes the end G to freeze up and become pin connected, determine the maximum horizontal force P that could be applied to the handle without causing either of the two rods to buckle. The member are pin connected at A, B, D, E, and F. So you can see this is the control linkage, and this is member B, E, and FG that is having diameter of 1 meter. So you have to determine the maximum load P that can be applied to this mechanism without causing either of the two rod to buckle. So let's start with the solution. Now from this diagram you can see if you applied load, so this lever will move in this direction causing the force to on FBE on this direction. As a result, if you take this vertical column as a free body diagram, so FBE will be exerted in this direction. So I will take the free body diagram of this only, and on this diagram only FBE is causing force toward left hand side. So you can see here I have drawn the free body diagram. So this force will be FBE, and we are interested to find out this FBE. So how we'll find this? So by using equation of equilibrium, that sum of all movement about point A is equal to 0, taking the counterclockwise movement as positive. Also you can see there is a pin support at point A. So if you remove this pin support, so you will be having a vertical reaction force which is AY, as well as there is a horizontal reaction force which will be represented as AX. So let's apply this equation of equilibrium. Now about point A, the first force which is producing movement is this P load, and perpendicular distance is 12 plus 4 is 16, and this is producing clockwise, so it will be negative. So we can write it as P multiplied by 16, that is negative. The second force that is producing movement is FBE, and perpendicular distance is this 4 inch, and this is producing counterclockwise movement, so it will be positive. So I can write it plus 4 multiplied by FBE. There is this, as these forces are passing through point A, so they are not producing any movement, so the sum of all this movement about point A is equal to 0. So it means that 4FBE is equal to 16 times P, and FBE will be equal to 4 times P. Okay, now we have this FBE. So what we are going to do is that you can see the forces in this member is 4P, and that is equal to FBE. Now this load is transferred to this member and this member as well. So what we are going to do is that the load acted upon by this member on this is on the left side, while on this member it will be on the right side. So I will take the free body diagram of FED, and that is shown over here. So what we will do is that we will represent the force in this direction. This is FBE, and we are interested to find out the force in FG. So you can see that this load is causing this member to move in this direction, causing the compression in FG. As a result, FG will apply force in this direction. So we will represent this force is FG, FFG. And at point D, we have a pin support. So you can have a vertical reaction DY as well as horizontal reaction dx. Now we will find this force FFG in this vertical column FED. So we will apply equation that sum of all movement about point D is equal to 0, and taking the counterclockwise movement as positive. So about point D, the first movement is due to this FFG into perpendicular distance is 4 plus 2, 6 inch, and that is counterclockwise, so it will be positive. So I can write it FFG into 6 The second moment is due to this FBE force and perpendicular distance is 4 inch and it is producing clockwise movement, so it will be negative. Minus this FBE multiplied by 4 is equal to 0. So 6FFG is equal to 4 times FBE, and we know that this for FBE is 4 times P, so 4 multiplied by 4P is equal to 16P. So when you solve for FFG, so that will be equal to 16P divided by 6, and you will get this FFG will be equal to 2.667P. Now we have forces in member FBE which can be seen that it is compressive, and similarly this FFG that is also incompressive. So what we will do is that we will find the critical load for each. So let me write for rod BE, we know that critical load P critical is equal to pi square EI divided by LE square, where LE is effective length. LE is equal to KL. And what is K? Since you can see these both members are pin ended, so I will go to the book and you can see here for both end pinned. This is for the case 1, you can see both ends are pinned, so K is equal to 1. So I will write K is equal to 1 for both end pinned and pinned. So what will happen that our this equation P critical will be equal to pi square EI divided by KL whole square, and that will be equal to pi square EI divided by L square. Okay, so we will have to put the value over here. So I will put P critical will be equal to pi square. So pi is 3.1417 whole square. What is the value of E? So you can see for L2 steel rod, we will write the value of E from the end of the book as well as for the critical load. So I will go to the end of the book, average mechanical properties. So here you can see, let me show you, this is L2 steel alloy. So E is 29 into 10 raised to power 3 KSI, and yield strength is 102. Tensile yield strength is 102 KSI. I will note down these two values. So E is 29 into 10 raised to power 3 KSI. What is I? So I for circular rod is pi by 4 D power 4 and pi by 4. And what is the value of diameter? Diameter is 1. So I formula is pi by 4 r power 4. So I will write radius will be 0.15. So 0.5 power 4 divide by L square. So effective length for BE is 15 inch. So 15 square. Okay. Now for this member BE, we will take this P critical is equal to 4P because force acting is 4P, and for the member BE not to buckle, this P critical will be equal to 4P. When your 4P is greater than critical load, so it will be buckle. So put the value of P critical in this equation, so you will get this 4P is equal to 3.1417 whole square multiplied by E, which is 29 into 10 raised to power 3 multiplied by I, which is pi by 4 multiplied by 0.5 power 4 divided by 15 square. So from here you will get this P will be equal to 15.6 K. 15.6 K. Okay, so this is the load which will not produce any buckling. Now for Euler formula verification, we will also check whether this load is producing any buckling or not. So we know that for Euler formula verification we have critical stress, sigma critical should be less than sigma yield. So how we will find this critical stress? So we will take this critical load divided by critical area is less than sigma yield, and sigma yield, if you remember from the table, that was 102 KSI. Now put the value of P critical, and P critical is actually 4P divided by area. So area is pi by 4 d square, and that is pi by 4, diameter is 1 square. That should be less than 102 KSI. Okay, so we can write it as 4 multiplied by 15.6 divided by pi by 4 power 1 square is less than 102. And when you solve this left hand side, so what you will get is that is 79.5 KSI, and that is less than 102 KSI. So it means that this load P that is calculated is okay. Now what we will do is that we will move toward for rod FG, and again we will find the P critical, and we know that P critical is equal to pi square EI divided by LE square, where LE is equal to K into L. And for this rod, let me show you that this FG is also both end is bent, so with a compressive load, so K will be equal to 1. So I will write it that effective length L in this case will be equal to L, and P critical is equal to how much? Here we have calculated load in FG is 2.667 P. So 2.667 P, because this your load should be equal to P critical for the member to not buckle. If your load is exceeding the P critical value, so it will buckle. Now what you will do is that 2.667 times P is equal to pi square multiplied by E, which was 29 into 10 to the power 3. I was pi by 2, 0.5, pi by 4, 0.5 power 4. This is not 2, this is 0.4. Divided by effective length. So effective length can be seen over here is 20 inch. So I will write it 20 square. Okay. So from here, when you calculate this P, so this P will be equal to 13.2 K. Okay. Now this is the load in due to member FG that should not buckle. So we'll also check for Euler verification. So we know that critical stress is equal to P critical divided by critical area. So P critical here in this case is 2.667 times P divided by critical area, and that is 2.667 multiplied by 13.2 divided by area. Diameter is given as 1, so pi by 4, 1 square. Okay, that is critical stress, and when you solve this, this will be 44.7 KSI. So as your critical stress is less than yield, which is 102 KSI, so this load is also okay. Now remember that you have two loads, P is 15.6 and P is equal to 1.13.2 kips. So maximum load P is equal to 13.2 kips will be our answer for that can be applied on this mechanism that will not produce any buckling in member B, E, and F, G. The reason why we have selected this smallest value 13.2 because you can see this load will also satisfy this criteria as well as this criteria. If you put the value, it will satisfy it. But your this load 15.6, if you choose and put it over here, clear here, so your critical load will in this case, okay, so it will increase. Or simply you can see you have to choose the smallest one in order for the safer design. And this was all about this problem 13-12. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.